All right, this video is based on section of finding limits graphically and numerically. So the first thing we're going to do is work our way to the explaining what a limit actually is, and then we'll see how to handle them graphically, numerically. Now suppose you have a function f of x is defined as x squared minus 4 divided by x minus 2. Now if a function's written that way, you might think, can't you just factor that numerator and cancel it out? Not really. Not for the purposes of determining the domain of the function. In other words, if it's written in this particular form, x cannot be 2. Now you'll see here shortly, graphically, it's going to be the same as if you divide that, but except for the fact you definitely are going to have a gap there at 2. So f of 2 is for sure undefined. Now, let's look at the evaluating function values of x near the vicinity of 2 and look and see what happens going on graphically. Or numerically, I should say. Okay, f of 2 would be undefined, but let's look at some values as x approaches 2. We'll look at it coming from values smaller than 2, 1.9, 1.99, 1.999. So basically these values, and I have this little table right here, and there's y1 in the calculator, so that's where I got these from. So you can see those are the y values from putting those x's into the f of x. Now let's look on the other side of 2. 2.001, 0.1, 2.1. And you can see those results, those y values. Now notice as we're approaching 2 from values smaller than 2, coming from the left to the right at 2, and then coming from larger to smaller. You see it getting closer and closer to 2 without actually reaching 2. And you can see from here that notice that both directions it's getting closer and closer to the value of 4, correct? And you see it's getting close to 4 both sides. So what we're saying right here is the value for f of x approaches 4, y is approaching 4 as x approaches 2. See, it's never exactly hitting 4, but it's approaching it. And that's basically the concept of a limit. That's what, limit, we'll see cases where the limit value and the function value are the same. But this is a good example where the limit technically will exist, even though the function value does not. So let's look at, now I graph this. So graphically, now I don't know if I zoomed in on the calculator or not, but notice that I just, even though it's still x is not equal to, for graphing purposes, I cancel that out and left it as x plus 2. So as I said a couple minutes ago, that it was going to be the same graph as the original function reducing to x plus 2, but you still have that undefined value at 2. Factoring and canceling does not eliminate that fact that x is undefined at 2. So there's what it looks like. It's basically the line y equals x plus 2, but not defined at 2 for x, and then of course 4 for y. Now, if you look at the calculator, you can see sometimes it sees in a calculator, though, you really have to zoom in or adjust your window. And these calculators are great, but sometimes there's special circumstances where you have to be skilled as a user to kind of know what you're looking for there. Now the calculator does not put a circle in there, but it's got a gap right there between the line segment breaks up right there. That's equivalent to this hole right here. Now notice as x is approaching 2 from the left and x is approaching 2 from the right. So what I'm doing is, so as these values are going up and down, you're still approaching horizontally at 2. So we're just looking at what the y is doing. But as these are approaching 2 from the left and the right, you see it's approaching where that hole is. And the hole is at 4. So this is the notation that we use. Limit as x approaches c of f of x if it equals L if it's approaching that same value from both sides. So in this case, L would be 4. So L is only if your limit exists. If it approaches 2 different values, it's not going to exist. But if it exists, L is just representing the numerical value of what the limit would be. So we read this as the limit of f of x as x approaches c will equal to L if it exists. So it's quite common. Limits can certainly not exist. We'll see that. So here's the notation then. So the limit as x approaches 2 of x squared minus 4 over x minus 2 would equal 4. The limit would, because it's approaching 4 from both directions. However, f of 2 is still undefined. So we're indicating here that if it exists, it will approach some value L from both the left and the right directions. It's got to be heading toward the same point. It can't be going different directions or different values from each direction. Now here's one. Cosine of limit as x goes to 0, cosine of x minus 1 over x. Now f of 0 would clearly be undefined here. If you put 0 in here, cosine of 0 is 1, 1 minus 1 is 0, 0 divided by 0 is undefined. You cannot divide by 0, so even 0 divided by 0 is undefined. So no doubt that f of 0 is undefined, but the limit might exist at 0. Now the x values you want to use, you want to put your calculator in radian mode when you do this. I just sort of filled the number. Oh, I did it over here too from the calculator. You can see. Anytime you get the e to the negative whatever, that's just scientific notation. You just move it 4 decimal places over to the left. So like for example 5e to the negative 4 would be this number right here, 0.0005. So you take these values and then fill this chart in, looking at it from both sides. You see they're getting smaller and smaller and smaller. Well, it's safe to say that it's approaching 0 because they're getting smaller both sides. So we say f of x approaches 0 as x approaches 0 from both directions. Now, especially radian mode is important when you're graphing. You always want to graph in radian mode. Now, I just put a big, artificial circle there. Obviously the calculator does not show the circle, but it would come through here and it would leave a gap, a hole right there, which when we write them by hand, we put that circle there. So this graph is as x approaches 0, y is approaching 0. It's basically approaching the origin. Excuse me. So that limit would actually have a value of 0. I mean, as x approaches 0, y is approaching 0. Now, how about this one? The limit of the absolute value of x divided by x. So f of 0 would clearly be undefined here because you would have to divide by 0. You can never divide by 0, even if 0 is on top. Now, I put this in here to evaluate function values. Now, for this one, notice that any negative value you put in here for that particular function is going to produce a y value of -1. Any value that you put that's positive into this expression right here, you're going to get +1. So as you can see, coming from the left of 0, approaching 0, it's all -1 values. Approaching from the right, coming to 0, is all +1. So you can see that they're not converging on the same number from both sides. And the UND just stands for undefined. Function value undefined at 0. So graphically, what we've got going on, I just said ignore that little dot that put there. They put that there. That's not really needed. But you can see as you're coming along here, use a different color, yes. As you're approaching, you're coming along that path, and then you're coming along this path. They're not converging at the same place as the other two problems were. They're not merging into the same path. So what that means is this limit does not exist. And you'll see that I'll use the shorthand notation. DNE we use for does not exist. Now this book goes into all these formal definitions of limits. I don't test that, but if you want to read up on that, perhaps if you plan on studying more theoretical mathematics later in your career or something, you might be interested in that. Most engineers and science majors would have no need for this, but it's sort of the mathematical existence and uniqueness argument that justifies these limits or exist or say what they say. In other words, we're doing these problems correctly and we're using the correct logic, but this is sort of like the proving of it being right. That's all. So it doesn't affect anything that we're doing whatsoever, other than just the mathematical reasoning behind it. Now here's another one. Limit as x goes to 0 of tan of x over x. That's going to get divided by 0. So we definitely have f of 0 is undefined. And you can see now these values, because it's not, and I did this over here. If you do function values in a calculator, let's see if I have a y in there. Oh, okay, well, I have y equals x. Let me make it at least something like x squared. I don't know if you ever use this thing here. You go vars, y vars. That's how you do just a specific function value. Y1 if we're using the first function. So this basically, I changed that to x squared. So y1 of 3 basically is evaluating 3 squared. There you go, 9. So there's how you can just do f of a single number without having to use that table thing, right? The table, all that kind of stuff, table set. Yeah, you can just do a single value. But what I did here is to show you that that's because of the number of displays of decimals. Those ones really aren't ones, but they're just showing them as one due to rounding. So what I did, I just came over here and I put y of 0.001, which is right here, and shows 1, but that's really what the value is. It's not exactly 1. Not that that matters that much. I just wanted to show you. So these don't really equal, unlike the absolute value one I did a minute ago, where they were either exactly -1 or +1. But anyway, taking that aside, I just drew it this way. It's kind of like, left to right. Now it's just written up and down because of the way, this table is displayed. Obviously, if the table was displayed horizontally like I was doing above, we would draw the arrows left and right. So it's definitely approaching 1 from both directions. And so the limit's definitely 1. Now, Maple's not something you have to know or use in this class, but it's a very powerful mathematical software package. It's just, you may encounter it somewhere down the road, but I use it in Cal 1, Cal 2, and especially in Cal 3 with 3-dimensional graphs, but for all kinds of other stuff. But I'll bring up Maple and see what I was doing here. Some stuff that you're not quite ready for. This is one of these is Cal 1, the rest of these are Cal 2. But anyway, so it's very powerful mathematical software package that can do stuff. So I like to just put these kind of things in there just to verify the answers a little bit, But so Maple basically says that same problem is 1. So that probably means we're in good shape. Now let's look at this example. Limit as x goes to 0 of tan of x over tan of 2x. F of 0 would be undefined, of course. Tan of 0 on bottom, so it would be 0. Now, come over here, you put the values in, and you see it's approaching 0.5 from both directions. Okay, this one, I probably wouldn't put this on the exam, because I guess this is, keep in mind that these terms, these tans don't really cancel out. I know it's like x over 2x equals 1/2. That's just the way these functions work. So the answer is 1/2, technically, is approaching 0.5. But one thing very important, I'll say this now, to carry on with you mathematically, is, trig functions must always have an argument. So tan by itself doesn't mean anything. It's got to be tangent of something. So so I know it just looks like the tans cancel and you have x over 2x equals 1/2. So I assume it probably works at that. Okay, so But mathematically, anyway, based on what we're doing, plugging numbers in, I didn't graph this, but I guess I could, and it would certainly be approaching 1/2. Now, sometimes this technique's not so good for if it's approaching, limits don't have to always approach, pretty values. Like this next one, we're going to deal with this more in an upcoming section. But this one I would not use as a problem like this on a chart, a test or a chart problem, because there's an algebraic way to do this, to work this out, to get exactly 1/9. So, and you see there's maple. I typed it maple 1/9. See, that would be really, really hard to tell. This one would be using just numbers alone, unless you could see it was heading to 0.111111, which is 1/9. But yeah, so there's kind of a flaw in this technique, as far as it doesn't always work very well for weird answers. Like if you had a limit that equaled 11/16, you'd never be able to tell that from just using a table of values. So yeah, the table's neat. It's useful for certain situations, but it's just one way to do it, and graphically. So we've been doing these, looking at both of these from looking at the graphs. I didn't graph a couple of these functions. I didn't graph. Did I? Tan of x over x. You know what? I guess I could graph that real quick. Let me make sure I'm in radian mode here. I am. So I'm going to go over here, clear that, and I want to go tan of x divided by x. Now I may have to zoom in on this. Let's go graph. Obviously you may have to change the window a little bit. Oh yeah, tan has all those asymptote graphs and things in it. Anyway, well, yeah, I guess I could. I only have to do this between -2 to 2, so I'll just kind of change the window. We're only near 0 anyway. I guess I could have looked at it. Oh yeah, look at that's a wide range of x's there I didn't really need. And we already know the limit's going to be 1, so we don't need a lot of y values. I'll go from now 0 to 3, just something that includes 1. Now I'll graph it again. Now I'll paste it in here for future generations. Now, we could zoom in on this. I'm just going to say this verbally just to save time here. I could zoom in on that. Maybe I'll go back to the calculator and zoom in on it without actually putting the... Oh, I think I tried to open this twice here. Okay, no, but I'm just referring to the hole in the graph there. Now I can manually set these windows. I'll just kind of scroll down right where it is. It just looks like visually that it's continuous, but yeah, if you look real close, I think you can see there, right? There's a gap there. In other words, the function value does not exist at 0, but the limit did equal 1. That's the y value. Okay, that's all I wanted to show you for that one. So, because it can be kind of tricky. That looks like, hey, that looks continuous. It looks like the function value. Because we are going to see pretty soon that function values and limit values can both be the same thing. When the function doesn't have the discontinuity there. Now, suppose that we have this kind of problem. If we're going to look at a picture, and could we determine what the limits are from looking at the picture? Now, pretend like that the arrows aren't already drawn there for you, so you'll have to kind of ignore that or treat it as if you were drawing it yourself. So we have a couple questions over here. We're saying, what's the limit of f of x approaches 3? So we come over here for 3 for x. Now, ignore that dot. We'll talk about that dot in just a second here. Ignore that. The limit's going to be if it's approaching the same thing on a graph from both directions. See, this graph is approaching, as it approaches 3, it's approaching that hole, and then that hole value is at 2. Now, for problems like this, if this came up on a quiz or a test, that we're not going to try to trick you here. You can assume it's the nearest integer, even if the drawing's not perfect. I wouldn't put a picture like this on here and say, oh, well, the answer is 1.9 or something. You would assume it was the nearest integer. So it's approaching 3 regardless of that dot. Now I'll talk about that dot. The dot just means we have a function value. That just means f of 3, so it's asking f of 3 would be 1. It would be where the dot is. So like these other ones that had f of something, let me scroll back up here just for a second. I could take this graph and right here and just plop in a dot right here. Like that. Now, so f of 2 would now be defined if that dot was added there. F of 2 would be where it would be 1, where I just put that dot for the y value. So that dot means you're guaranteed to have a function value. That's all that dot does. So, yeah, but notice it didn't affect the limit. Now, if that dot ends up being right here where the limit is, then they're both the same. Then the limit value and the function value would be the same. So that's what the dot's accomplishing there. It's giving us a function value. But it has nothing to do with the fact of where these green arrows are, where the green arrows are representing how the limit behavior is, how the function's behaving as you're approaching the graph. Now, how about the next one? Limit f of x. So you see the green arrows, it's approaching 0. Definitely 1. F of 0 is 1 because the function value is there. So anytime the function value is where the limit is, they'll equal each other. That'll sort of be more formally defined in an upcoming section, but that's, yeah. So if it's smooth and continuous like that, no gaps or holes or anything like that, the function value and the limit value will both exist, and they'll be the same value. How about this one? As x approaches 2, limit as x approaches 2, they're coming down here, and they're both, see these two green? They're both approaching that hole, which we will assume that hole is at -1. But g of 2, well, obviously it's a hole there, so it's not defined. So then I would just kind of look up and down this graph and see if I saw a random dot put in there somewhere. There's not a dot. So without the dot, that means g of 2 would be undefined. Now, let's look at 4. Limit of g of x as x approaches 4. You come over here at 4. Coming from the left, it's coming up here to the dot. From the right, it's coming toward the hole. They are not approaching the same thing. So if they're not approaching the same value, that means the limit dne does not exist. So notice the notation we use here, the wording, when it's a function value we don't have, we call that undefined. For limits, we generally use the phrasing does not exist. Now let's see if there's a function value. And there is. It's where the dot is. So g of 4, when x is 4, y is 2. But yeah, you could have had both holes here. They could have both been holes, and there would have been no function value. Now, they cannot both be dots because that violates something back in algebra called the vertical line test. So you could not have two dots there, because then the graph would not be a function. We would be lying to be calling it a, well, maybe not lying, but we would be wrong if we called it a function. I guess lying would be if you knew it wasn't. Okay, let's look at this picture. As x approaches 3, I just call this one h of x. This approaches 3, it's coming down, they're both closing in on that dot. That dot is at 1. So the answer would be 1. H of 3, there's no dot in there anywhere. Vertically, looking up and down, no dot, so it's undefined. Limit as x approaches 4 of h of x. They're both approaching two different values. You're coming from the left, it's approaching the dot, from the right, the whole. Disconnects, DNE, but H of 4 would be the Y value 3 when X equals 4. And that's the end of this lecture.